Hello students, in this video I'll be explaining how to write and balance chemical equations which consist of both ionic and covalent compounds. In a sense, this is a culmination of the review work that we have been doing as a class for the past 2.5 weeks. So let's get started. Now what is a balanced chemical equation? As you can see, the definition is pretty clear. A chemical equation which has equal number of atoms of each element on the reactant and the product side. So let's try to understand this using an analogy. So let's say we have a chemical equation 2A plus B2 is giving you A2 B2. Okay, let's say this is a chemical equation, and let's say A and B are two different elements. All right, now the substances that you see on the left side of the chemical equation, so these substances are called reactants, and the substances, or in this case a single substance that you see on the right side of the chemical equation, this is called a product. Okay, so how to add up atoms on both the side? What you need to do is you need to multiply the number that's appearing in front, which is called a coefficient, with the superscript that appears alongside the symbol. So here there is no number. We know that that's basically signifying a 1. So the number of atoms of A on the reactant side is 2 times 1, which is 2. Now for the second reactant, there is no number that's written in front, so we assume the coefficient is 1. Alright, so again we do the same thing. We multiply the coefficient with the subscript which is associated with this element, and the number again turns out to be 2. But notice how the number came out to be 2 for both of these reactants due to different reasons. One had a coefficient of 2 and that was multiplied with the subscript of 1, and for the other it was the other way around. It had a coefficient of 1 and a subscript of 2. Now let's see what is the situation on the other side. So we have a single product here, and there is no number that's written in front of the product, so we assume that the coefficient is 1. So how do we get the total number of atoms of A and B here? Again, we multiply the coefficient with the superscript, with the subscript that's appearing for A and B. So for A, it's again 1 times 2, which is 2, and for B it's also 1 times 2, which is 2. So we see here that this is a balanced chemical equation because the number of atoms of A and B on the reactant and product side are the same. So why should chemical equations be balanced in the first place? So we have a principle which is called principle of atomic conservation, which states that atoms can neither be created nor destroyed in a chemical reactions. So if, let's say, our previous equation looked like A2 plus B2 gives AB. Let's say it looked something like this. Okay, so now if you try to add up the number of atoms, they won't. So for A, the number of atoms would be 1 times 2, which is 2. For B, again, it would be 1 times 2, that would be 2. But the coefficient here is 1, right? And the subscripts for A and B are also 1. So for A as well as B, the number of atoms on the product side is 1. So what this means is that one atom of A and one atom of B is getting destroyed in a chemical reaction, which is a clear violation of the principle of atomic conservation. So that's the reason why chemical equations should be balanced. This is basically an extension of law of conservation of mass. So let's try with one of the simplest example of how to balance a chemical equation. We'll use our understanding from all the modules and worksheets that we have done so far. Okay, so now hydrogen. We know that hydrogen is a non-metal. But if we just write hydrogen as H, that would be wrong because we know from our previous tutorial that hydrogen exists as a diatomic molecule, that's H2. And the same goes for oxygen. Oxygen also exists as a diatomic molecule, so it's O2. And the formula of water is H2O. So we have the basic skeletal equation now, all right? And now we need to verify if this equation is balanced. So again, we know if nothing is written, the coefficients are 1. So the coefficients are 1 for all the reactants and products in this equation, right? So the number of atoms of hydrogen comes out to be 1 times 2, which is 2. The number of atoms of oxygen also comes out to be 1 times 2, which is 2. Now on the product side, again the coefficient is 1. So the number of atoms of hydrogen is 1 times 2, which is 2. But the number of atom of oxygen comes out to be 1 times 1 because we see the subscript associated with oxygen is 1. So it's 1 times 1, which is 1. So here, while the hydrogen atoms are balanced, the oxygen atoms are not. Okay, now here is the important thing. You could simply say that, okay, let me just put a 2 as the subscript here and the equation is balanced. But this would be wrong because by putting a 2 in the subscript, you essentially change the identity of the substance itself. So when you put this 2, this is no longer water. This is basically a different chemical substance called hydrogen peroxide. So in essence, you cannot balance a chemical equation by putting a number in the subscript. The only thing that you can manipulate are the coefficients here. So initially all the coefficients are 1, right? But we know that since oxygen is unbalanced, we need to make up for the unbalanced oxygen atom. And we can simply do that by putting a 2 here. So if we put a 2 here, okay, so now we have the coefficient of oxygen as 2 and the subscript as 1. So the number of oxygens are balanced. But this 2 also needs to be multiplied with the number of hydrogen atoms, because if we put a 2 in front, not only is it multiplied with oxygen, but it's multiplied with hydrogen as well. So this alters the number of hydrogen atoms on the product side as well. So this becomes 2 times 2, which is 4. So while we were able to balance oxygen, the number of hydrogens in the process got unbalanced. But I think this is an easy fix. If instead of having a coefficient 1, we put a coefficient 2 on the reactant side for hydrogen, the number of hydrogens also become 2 times 2, which is 4. So now we see the number of hydrogen on the reactant side is 4. The number of hydrogen on the product side is also 4. The number of oxygens on the reactant side is 2 atoms, and the number of oxygen atoms on the product side is also 2. So here we get a balanced chemical equation. One important note, you don't need to show the coefficient 1. It's understood that if no coefficient is there, it is 1. So the balanced chemical equation becomes 2H2 plus O2 gives you 2H2O. Let's go to the next example. So if you think you're confident enough to do this on your own, you can pause this video here and then compare your working with my final answer. Alright, so nitrogen needs to be depicted as N2, hydrogen needs to be depicted as H2, and ammonia needs to be depicted as NH3. This is a formula that you need to commit to your memory. Alright. Now let's compare the number of nitrogen and hydrogen atoms on both sides. So here on the reactant side you have 1 times 2, which is just 2 nitrogen atoms. You have for hydrogens again 1 times 2, which is 2 hydrogens. And on the product side, the number of nitrogens are 1 times 1, because you can see that the coefficient, there is no coefficient mentioned, so we assume the coefficient is 1, and there is no subscript with nitrogen, so we assume that is also 1. And the number of hydrogens are 1 times 3, which is 3. Okay, so we see that none of the atoms, nitrogen or hydrogens, are balanced here. Okay, so how do we fix this? In questions like these, the first thing that you should try to do is try to make the atom with odd number into an even number. All right, so we have 3 hydrogens here. So what we do is we try to multiply it with the smallest number to make it even. Okay, so you can have 2 here. Some might even argue that we could also explain it like having 2 nitrogens on the left side and having only 1 nitrogen on the right side. So again, you just multiply this with 2 to get 2 nitrogens. So both the approaches are fine. Okay, so now we have um, the number of nitrogens on both the sides being balanced. So 2 times 1, which is 2, and the number of hydrogens has also increased, so that's 2 times 3, which is 6. Now the number of hydrogens on the reactant side is still 2, but if you put a coefficient 3 here, okay, so that fixes the number of hydrogens, so this also becomes 3 times 2, which is 6. So now we have a balanced chemical equation with 2 nitrogens on both sides and 6 hydrogen atoms on both sides. Let's see another example. So here we have iron reacting with hydrochloric acid and makes iron 3 chloride and hydrogen, right? So let's see how we can write a chemical equation for this one. So iron is a metal and all metals are represented by just the symbol, which is Fe. So it doesn't exist as a molecule like Fe2. We know from our prior knowledge that hydrochloric acid is HCl, right? And the product formed is iron 3 chloride. So we know that iron here has a valency 3 and chlorine is in group 7, so chlorine has a valency of 1. So if we cross multiply, the formula of iron 3 chloride comes out to be FeCl3, and we get hydrogen gas, which we know is a diatomic molecule, so that is H2. Alright, so this is our skeletal equation. Okay, so now how to actually balance this equation? The first thing that perhaps you might think is that, okay, the number of iron atoms are balanced, so this is 1 and this is also 1, while the number of hydrogens and chlorine is unbalanced, so chlorine is 1 here, but chlorines are 3 on the product side and the number of hydrogens are 2. So Some of you might think actually that, okay, let's multiply the number 3 with HCl, but if we do that, that's going to make the number of hydrogen atoms as 3, but we have 2 hydrogen atoms on the product side. So what's the solution for this? It's quite easy. Again, just as I suggested in the previous slide, when you have an odd number, try to make it even. So when we have 3 chlorines here, what we'll try to do is we'll try to make them even. And we try to make them even by multiplying with the coefficient 2. Alright, so we have 2 ions now because this is multiplied with the number of iron atoms as well. And now the number of chlorine atoms has changed to a 6, right? Now, since we have 6 chlorine atoms on the product side and only 1 on the reactant side, what we do is we multiply this with a coefficient of 6 so as to get 6 chlorine atoms. Okay, but that also changes the number of hydrogens, but as you can see, this is quite manageable now, because if we have 6 hydrogens here, all we need to do is put a coefficient 3, and that makes up 6 hydrogens as well. And lastly, since there are 2 ions now on the product side, what we can do is have a coefficient 2 here as well. So the balanced chemical equation becomes 2Fe plus 6HCl gives 2FeCl3 plus 3H2. By the way, I just wanted to make one thing clear. This is a hypothetical chemical reaction. In reality, when iron reacts with hydrochloric acid, it makes iron 2 chloride instead of iron 3 chloride. But I just wanted to give you a sense of a more complex chemical equation. That's why I came up with this example. All right, let's try to balance this word equation now. So first we write the chemical equation, which is CaOH whole twice. That's the formula of calcium hydroxide plus hydrochloric acid. The formula is HCl, giving us calcium chloride, which is CaCl2 plus water, which is H2O. So hopefully you were able to arrive at the chemical equation on your own. Okay, so now let's try to write down the number of atoms of each element on both the sides. So on the reactant side, there is a single calcium atom. Okay, as for the number of oxygen atoms, we see that hydroxide is a polyatomic ion here, which has a 2 after a parenthesis written as a subscript. So that means this 2 is multiplied with oxygen as well as hydrogen, which means the number of oxygen atoms is 2 on the reactant side. The number of hydrogen atoms is a bit complex because hydrogen is existing here and here as well. Okay, so in calcium hydroxide, clearly the 2 gets multiplied with 1, so the number of hydrogens in calcium hydroxide is 2. But then we also have a single atom of hydrogen in hydrochloric acid, so that makes up 3 atoms of hydrogen on the reactant side. And finally, the number of chlorines is also 1. Similarly, let's make a list of all the atoms of different elements on the product side. So we have a single calcium atom, which is quite obvious, and then we have one oxygen atom because there is just one oxygen present in the water molecule. We have two hydrogen atoms present as H2, and then we have two chlorine atoms. Okay, all right. Now, just as discussed in the previous video, having odd number of atoms on either side makes things difficult. So the easy way around is to put a 2 here because that would make the number of hydrogen atoms even. Okay, so having a 2 here means that the number of hydrogens is no longer 3, but the number of hydrogen atoms are 4. And in that process, we were also able to balance the number of chlorines. So this 2 multiplied with Cl balanced the number of chlorines as well. Okay, now we have 4 hydrogen atoms on the reactant side, but on the product side, we just have 2. So what do? We multiply the number of hydrogens by having a coefficient 2 here. So that makes 4 hydrogen atoms. So the number of hydrogen atoms also get balanced. And the number of oxygen atoms in the process also gets balanced, because this 2 not only is multiplied with the H2 but is also multiplied with a single oxygen atom. So here we can see this is our final balanced equation. CaOH whole twice plus 2HCl gives us CaCl2 plus 2H2O. Pause the video and rewind in case this balancing was not clear, and seek clarification if it's still not clear. Alright, let's now do the final example, which is aluminum hydroxide reacting with sulfuric acid to give you aluminum sulfate and water. So I'm assuming you will be able to write the chemical formulas of all the reactants and products on your own. So I'm just going to directly write that. ALOH whole thrice plus H2SO4 gives us Al2SO4 whole thrice plus H2O. Now, here is an important detail which makes this balancing a little different from all the other previous examples. You see here that a polyatomic ion, that is sulfate, appearing on both sides. So when you see a polyatomic ion like sulfate in this instance appearing on both sides, you don't need to treat sulfur and oxygen in sulfate as different atoms. You need to treat sulfate as one entity. That's going to help you balance the equation more quickly. Okay, so keeping that in mind, let's make a list of atoms of each element on both the sides. So on the reactant side, we have one atom of aluminum. Okay, and now for the hydrogens, we see that there are 3 hydrogens in the hydroxide part of aluminum hydroxide, and then we have 2 hydrogens here. So that makes a total of 5 hydrogens on the reactant side. We also see that there are 3 oxygens that are present in the hydroxide. Of course, we'll not be considering the oxygens in the sulfate, since we'll be treating sulfate as a single entity. So the number of sulfate is 1. Okay, let's now calculate the number of atoms or ions on the product side of the equation. So we have 2 aluminums. As for the number of hydrogens, we have 2 hydrogens, which is present in water. And then we have 1 oxygen that's present in water, excluding the oxygen that's present in sulfate. And then we have 3 sulfates. All right. Now, if you think you would be able to balance this equation on your own, you can pause this video here and then compare your answer with mine towards the end. All right. So there are two approaches to this. We can again use the approach of having uh, the number of odd number of atoms to be converted to evens, or we can go ahead with the approach of balancing the aluminum first. So let's balance the aluminum atoms first. So if we see that on the right side we have two aluminums, we can just multiply 2 here. Now this actually also converges well with the odd numbered approach, because here we see that if we multiply the number 2 with AlOH whole thrice, it also changes the number of hydrogen atoms here to 2 times 3, which is 6. So that changes the number of hydrogen atoms to 8 over here. I hope you're able to get the picture. Similarly, that also changes the number of oxygen atoms. So here, the number of oxygen atoms changes from 3 to a 6. All right. Now, the number of sulfates on the right side of the equation is a 3, but the number of sulfate on the left side of the equation is just a 1. So what do? We multiply the left side of the equation of the sulfuric acid part of the equation with 3, right? So when we do that, the number of sulfates also come out to be 3, and it changes the number of hydrogen atoms as well. So we already had 6 hydrogens from here, and now we have 6 hydrogens from here. So that makes a total of 12 hydrogens. All right. And now, since we have just 2 hydrogens here, what we can do is put a 6 here. And if you put a 6 here, that balances the number of hydrogens, but it also balances the number of oxygens. So now we have a completely balanced equation, which is 2AlOH whole thrice plus 3H2SO4 gives you Al2SO4 whole thrice plus 6H2. Hopefully this video was helpful for you to understand how to balance chemical equations. This completion of this module will not ensure that you have mastered chemical equation. You have to master chemical equation by consistent practice. But hopefully this video was useful. Thank you so much.